Hello, Tuesday, January 23rd, 2024. Time to get started on problem 19, the last problem of section 3, which has been quite a lot of work. It seems in this problem we'll be deriving such a bound that I was actually missing or needing to solve problem 17. So here we are. Well, we have this sum, so let's try to see what we get. All right, so this is bounded by as long as y is positive. That doesn't show that the sum is, we need to, I don't know what we need to, maybe we should put a bound on this. But that requires a bound on an, which we have not. Oh, it's FDA. And I also used the summation formula for FDA without thinking about it. Well, let's look at the ANs. They come as Fourier coefficients. I'll just have to find the exact formula. It's modulo h, th, so we go from 0 to h. I'll just write something, I think. And then some constant here I forget. I'll just find the correct expression. It turned out I didn't have it anywhere in my books, so I derived it by myself and believe this is the thing. And that means it's 1 divided by h. And then this is it. Oh, now I forget what I needed it for. That's to put a bound on the coefficients here. Of course, when f itself is a smooth function, holomorphic, then it's infinitely often differentiable, then this sum converges absolutely. And we also have some strong bounds on this, which I don't know. We will be deriving some of them, it seems. So f has a maximum value here. That seems to be enough. So the maximum value and then it's dx here. So this is obviously bounded depending on epsilon. Not only that, we can even put a bound so it decreases exponentially with n. Now what we already have this, so the sum is 1 divided by, well, let's put that outside. So this is bound C, not the C we're looking for here, so it's called C1. And then let's put that into this summation formula. We get it twice. This is a little weird. Actually, the definition of an has a minus, and here it's a plus. Minus minus, that gives a plus. So that's a power guy. So an, that's C1 times this. And then this guy to nth. And that is, we gave epsilon minus y. And what did we have to show? We have, of course, y is larger than epsilon, meaning that this is negative. I'll just have to write up the sum here, the power series sum. There's something wrong. Oh yeah, that's a negative coefficient. So this is smaller than 1, but it should hold for all y larger than epsilon. And we get this in here. So I need to put that into a constant, but if y can be as close to epsilon as we care to, we'll just say larger than epsilon plus something, a little thing, or times 1.01, then we could bind it. The way I've done it, when y tends to epsilon, this tends to unity, and this tends to naught, so it doesn't work. And it must obviously, it must hold for all values of y. They didn't read that x and y be real, but that's obvious. Yeah, time for a break. I'll see if I can find a way to prove this as is. Otherwise, I'll continue with the caveat that we need y a little larger. Oh, instead of this epsilon, we could use epsilon halves. Then that's of course that's the easy way to do it. I just chose an epsilon here, and we need just to choose half the value of epsilon, and then we are through. Then this will be bounded away from unity, and this will be bounded away from naught, and then we can put it into the constant. And that was epsilon halves. I'll just do it on paper by myself, and then I believe that will solve A. I believe my idea will work. So we go on with 19b, where a function is defined this way, and we have to compute this guy. So first it's f of gamma z we need to worry about, and it's cz plus d minus kth f of gamma z so we need to work on this. The absolute value, that should have been more vertical. Oh no, now let's see. Yeah, let's work on this. It's a little weird. Let's split it to the real and imaginary part. So we write z as x plus I y, where x and y are real. Now, I think I've misunderstood this totally. It's g of gamma z, so this is a real function which we operate on, and then per definition, so I think this was all wrong. And was that what I had to show? Oh, sorry, that was a trivial question and I thought it was complicated. Show that it is bounded on F. But then we just choose epsilon equal to 1/2. And then it's bounded this way. And exponentially. And this part is only bound polynomially. So of course it's bound absolutely. Because in F, the imaginary part of y is larger than or equal to square root 2/2. That was B and C. So it's bounded on I'm still confused about B here. So that is, we have to show that f of z gamma no, it's g of h. Oh, it's fj, yeah. Of course, it's only a problem as z tends to naught, or tends to the cusp. I'll just write it on paper because I get confused with the new notation here, and these guys, which are the ones we want to show are bounded, or rather, yeah. So I'll just do it by hand and then show the result. Just to show you how to do part A. This sum adds absolutely because f is holomorphic, so it's twice differentiable, so it holds with a Hölder condition. With alpha being unity, which is larger than 1/2. Therefore, this sum adds up, or rather this sum adds up absolutely. So this means this is right. And we can just write a few terms. Let's take, it starts with n equals 1, so we can put 1 outside of the parenthesis. If we call this g of I, then this sum is finite, so we can just, and it's decreasing, every term is decreasing, so by assuming y is larger than epsilon, this is smaller than or equal to some constant, C. So that's how simple part A is, if you can keep your head cold.